Okay, so first we're going to prove or use de Morpham's theorem to express cos 3 theta as a polynomial. So we have cos theta plus I sine theta cubed by de Morpham's theorem is cos 3 theta plus I sine 3 theta. So that means cos cubed theta. Let's see, 1, 1, 1, 1, 2, 1, 1, yeah, 3, 3, 1, yeah. Plus 3 cos squared I sine theta plus 3 cos theta I squared sine squared theta plus I cubed 3, 2, 1, and 0. Yeah, plus I cubed sine cubed theta. That's equal to cos 3 theta plus I sine 3 theta. We're only going to look at the real parts here, so I'll ignore that imaginary part and that imaginary part and that imaginary part. So now we have cos 3 theta is equal to cos cubed theta plus 3, and actually a big I squared's minus, so that's minus 3 cos theta, and sine squared is 1 minus cos squared theta. So that's cos cubed theta minus 3 cos theta plus 3 cos cubed theta. So that's 4 cos cubed theta minus 3 cos theta. That's what it looks like. Minus 3 and plus 3. Yeah, I think that's okay. It's kind of nice if they give it to you in the question, so you know if you got it. But provided I didn't make any algebraic slip, that looks okay to me. The second part here is quite tricky, though. Prove that it's always possible to do this, basically, for cos n theta. That's really tricky. So let's see if I can prove this. Cos theta plus I sine theta power n, that's equal to cos n theta plus I sine n theta. So I'm thinking if I expand on the left using the binomial theorem, let's just see what happens. N C0 cos n theta plus, well, I guess I should just write it out in the summation notation. Summation notation. So this is the sum or from 0 to n, and it's NC or times cos n minus or theta plus I sine, cos, oh yeah, sorry, that's not the sign, that's the multiplication, times I power n minus, or sine power or theta. That's equal to cos n theta plus I sine n theta. Let's just double check that. That's definitely an or, an n. and that's the OR that goes 0, 1, 2, 3, 4, 5 up to n. And this one here, I like to start from n, so n minus 0, yeah. And this one starts from the 0, yeah, so that looks okay. Now, if you look at the I power OR, that will equal I0, I1, I squared, I cubed, I power 4, which will equal 1, I minus 1 minus I, and then it begins again. 1, I minus 1 minus I. So you can note that if you were to only look at the real part, so the real part here equals, oh, don't quite have enough space here. That's equal to the real part here, cos n theta plus that. The real parts here happen when OR is 0, or 2, or 4, or 6. So this becomes then the sum. OR is 0 to n, but also that the OR is even only. So you skip the odd ones. That's n, c, OR times cos n minus OR theta times I OR, and then sine OR theta equals cos n theta. Now, since OR is even, let OR equal 2k. So then you get cos n theta is the sum, and k goes from 0 to n over 2. So we have, and I'm replacing the OR with 2k. So like, for example, if let's say like this went up to the 6, we only would need to have the even ones, which is 0, 2, 4, and 6. So we could do it using k. That OR is equal to 2k. So this would be n c OR, which again we're calling 2k. And k doesn't have to go all the way up to n. It only has to go to n over 2 because you're multiplying it by 2. Times cos n minus 2k times I power 2k, and then that's cos, that's sine 2k theta. But here comes the trick. You could take out the 2. And because this is sine squared, you could say it is 1 minus cos squared. So then this becomes the sum k 0 to n over 2 nc 2k times cos, oh, I left out my theta there, didn't I? Cos n minus 2k theta times I power 2k, and then squared. Oh, I did it the wrong way around. I wanted to take the k out and leave the yeah, I did that. I'll let me fix that. Did it the wrong way around. So here is 2k. What I'm doing is I'm taking the k outside the bracket, leaving inside sine squared. So then I can change sine squared into 1 minus cos squared theta, and that's k then instead of 2. So after all that work, we've shown that cos n theta can be written as a polynomial of cos theta, and this is the formula for it. So it is quite the tricky question, really. Quite the tricky question. I wonder, yeah. I wonder how many people would have gotten something like that. So, anyways, there you go. There's the proof for the second part here. Yes, quite the question.